I wanted to ask you, those of you who might be leaving before the end today, to do a favor for me once you get home, to send an email to admin. It's the email address on the PFQ webpage. Send an email to admin to tell us what you thought worked well at the workshop and things that maybe didn't work as well, and what you would want more of when we hold this again, which I think we'll be doing, and we're going to try to not hold it in January. Otherwise, for those of you who have to leave before the end, thank you for being here. We've had a blast, and we're still having a blast. Thanks very much.
I want to echo that. Thank you all for coming out. So my name's Stefan Preble, and I'm the chair for this session number 9, the first session of the day. And I'd like to introduce Professor Chris Gary from CUNY. Oops, just want to make sure.
Okay, thank you. Okay, I'll be talking about a topic I think is a little bit different than what most people have been talking about, having to do with atomic clocks, which is a very old subject. Although I did notice there's a poster up there that is closely related to some of the things I'm going to be talking about. So anyway, my interest is in the business of trying to increase the atomic clock precision and doing that with or without entanglement amongst the atoms involved in the atomic clock. And this work is funded mainly by the Air Force, but I've had prior funding from these other agencies that have funded work that led up to the work that I've been doing here. So. And my main collaborator in this project is Richard Baratella, who was a former graduate student of mine and has been postdocing with me ever since. And so let me get started here. Just a brief outline. I have a lot of stuff to present, so I'm going to try to get through this as much as I can. So I want to review the business of Ramsey spectroscopy, which is the basis of atomic clocks. And I want to talk about doing Ramsey spectroscopy with entangled atoms, the idea of the benefit of doing it using entanglement. Then I want to talk about Ramsey spectroscopy with N-atoms using atomic parity measurements, and I'll explain what that is. Then I want to switch. There's one thing I will talk about that has to do with photonics, I guess, is the interferometry using the photon parity operator, which is what I really worked on from the beginning. And then how we could maybe have an atomic clock based on the idea of atomic parity measurements. And then at the very end, if I have time, I'll talk about thoughts I've had about how you might actually do these measurements. Okay, so why are people interested in entanglement in this context? The main interest has actually been to perform quantum metrology for frequency standards using entanglement. So I won't go into this in a whole lot of detail, but the standard quantum limit is the best one can do. This I've really written down this in terms of photonic systems, but it basically works out to be the same thing. So it's the square root of the average photon number. That's 1 over the square root of that. That's what we call the standard quantum limit. 1 over n bar is the so-called Heisenberg limit, and that's the greatest sensitivity allowed by quantum mechanics as long as you have linear phase shifts, which is the only thing we've really considered. But let me talk very briefly here about the Ramsey method of separated fields. So for a single atom, you prepare a cavity which is being driven by a classical field. The same classical field drives both cavities, actually. The atom enters the cavity. It receives a pi over 2 pulse. It starts out in the ground state, gets put into the excited state, a superposition of the excited and ground state. And then you have another pi over 2, you have a period of free evolution, then you have another pi over 2 pulse at the other end, and then you do measurements on the population of the excited state. That's the basic idea about this. And let me do it a little bit more detailed here. So I've actually been thinking about this more in terms of ions, trapped ions, because that's where I came from when I got into this kind of work. But so if you have 2 levels with some frequency nu naught that you're trying to measure, or omega naught that you're trying to determine, or use as a frequency standard, then you have those 2 levels. And the procedure I just talked about, the business about the pi over 2 pulses, free evolution, and so forth, can easily be represented on the so-called Bloch sphere. And this is what it looks like on the Bloch sphere. The first sphere over there, all the atoms are assumed to be, the atom is assumed to be in the ground state. Pi over 2 pulse puts it on the equatorial plane. You let it freely evolve, and then you do another pi over 2 pulse, which presumably puts it up there at the North Pole, which is to be excited. So, and then you measure the probability that the atom is actually in the excited state. That's the basic idea. So just to show you in detail how it happens, I'm only interested in near resonance. Very far from resonance, we're not too concerned with here. So the omega naught is the frequency separating the two states. That's the frequency you're trying to measure. You prepare the superposition state, and then you let free evolution occur. And then you do another pi over 2 pulse, which just scrambles up the excited and ground states into superpositions of the excited and ground states. And the final state looks like the psi prime state that we have here. And then you simply calculate the frequency, the probability of the atom be in the excited state. And you get the cosine omega minus omega naught times the free evolution time, which is a key parameter in all this. And that's the signal for this. And if you calculate the problem, the two-level problem, in the full range where the very far off resonance frequencies contribute, this is what you get, and this is what they refer to as the Ramsey fringes. But we're only interested really in one Ramsey fringe. This is a function of the separation of the frequencies. And we're really interested only in the central fringe. So that's the only fringe that I'll consider from now on. And by the way, a key thing is the width of the fringe. And the fringe width goes as the inverse of the free evolution time. And so there are attempts to make the evolution time, the free evolution time, as long as possible to get narrower and narrower fringes. And I'll explain in a bit why we need that. This is stuff I said before in a different context. So the uncertainty of the frequency goes, for one atom, goes as the inverse of the free evolution time, but that's multiplied by 1 over the average, 1 over the square of the atom number when you do this n times, n atoms, in which case you get, that's the corresponding standard quantum limit here. And the detection technique is usually typically done by what's called Desmalt's electron shelving technique. I swiped this out of somebody's paper, and the label's a little different. So A is G and B is E. And the idea is if we're only interested in the population of the excited state, which is B in this case, then if you have another field that typically an optical field, will drive it up to level C, and then you look for the transition, the fluorescence from C back to B, and then that's how you detect it. The level from A, the energy from A to C is out of resonance or lacks along the parities don't match that you need and so forth. So that's how it's typically done. And here's my somewhat crude picture of an atomic clock, which I stole out of an old Scientific American. I couldn't find a decent picture of this sort of thing. And so the idea of the atomic clock turns out to be a lot simpler than one might think, at least the idea behind it. If you have a source of atoms, you send the beam of atoms through a laser which prepares the atoms, then you have 2 microwave cavities. By the way, the typical transitions involved here are hyperfine transitions from the F equal to 4, F equal to 3 levels of cesium. That's usually the one that you use, at least in some of these clocks. And these are all working in the microwave part of the spectrum. And the atoms have very long lifetimes in the excited state. It's on the order of 1,200 years in some cases. So anyway, so you prepare the atom in the state that you're going to use for the spectroscopy. Then you have microwave fields which give the 2 pi over 2 pulses, and the distance between the two microwave cavities determines the free evolution time, as does the velocity of the atom as it comes through. And they have a second laser beam, which is used for doing the detection, the day melt process that I talked about a few minutes ago. And this is all connected to a servo mechanism, which keeps the frequency such that you maximize the detection of the atoms in the excited state. That's what an atomic clock is really all about. And this is very old technology, because it really goes back to after World War II, in the late 40s and the early 50s, before even the transistor was invented. So this is very old stuff in some sense. But there's more reason now to try to find better atomic clocks, more precise, more stable atomic clocks, because the kind of measurements they want to do are not just to use it for timekeeping per se, but for practical purposes, it's going to be there for emerging technologies of the type that's been discussed here, but also in a very basic sense, because they're now planning to use atomic clocks to try to detect gravitational waves and also to test gravitational theories on a fundamental level. So a lot of interesting things going on here. So how do we improve the precision of atomic clocks and the stability of the clocks? And the idea basically is to make, the main approach has been to make the Ramsey fringes narrower. And one way to do that is to build what's called an atomic fountain clock, which is sketched here. And the idea here is you launch atoms upward under the gravitational field. The usual configuration is somewhat limited in what you can do, so for separation in velocities and so forth. So they launch the atoms upward, they go up, they get a pi/2 pulse on the way up, a pi/2 pulse on the way down, and this is what they've been doing. This is the kind of, there's a fairly sophisticated atomic fountain clock, for example, at NIST out in Boulder, and I'm sure there are lots of other places. In fact, the poster I saw out there had to do with this fountain business. Anyway, but now let me talk about the advantage of having more than one atom at a time and then actually having them entangled. So there are many possible states you could imagine. So the one I'm showing here, is the one where we have, I'm probably going to screw this up. Which one is the light? Is the pointer light?
Oh, it's not working.
It's not working?
Yeah, so you can use your mouse.
All right, I don't need it. All right, so the state at the top there shows two atoms that are entangled. That is, you can't factorize that state. Let's not worry about how you can get entangled states like that, because that's actually a bit of a problem, a challenge. But if you could have this thing evolve, if you could prepare that state and have it evolve freely, then you can see that the part that contains the free evolution time there has now a factor of 2. And if we could somehow then use a C0 gate to disentangle this state, which takes the E1, E2, and changes that into an E1, G2, then you can factorize everything, and then you get the probability of finding both atoms in the excited state. And now you get not 1 over T, but 1 over 2T. So you've reduced you increase the sensitivity by doing that. The problem is that what I'm hiding here is that in order to do this, you have to have these atoms actually be trapped ions, and you have to have a coupling with the vibrational mode, and the lasers that you use to create the vibrational mode and so forth have to be manipulated so you can get the mechanics of it. You have to have a James-Cummings type of interaction there to be able to prepare the states and also to do this manipulation of the C0. So it's a little bit more complicated than what I've probably indicated here. So anyway, that's the idea. And you can extend this to do N atoms. I got involved in this way back in 1998. And if you do that, you get an extra factor of N. And really, when you do this, you're approaching the Heisenberg limit of that. And so it's an improvement by a factor of 1 over the square root of N, over the Schott-Noyes or standard quantum limit. Around this time, in 1996, actually, Bollinger and this is actually Dave Wineland's group out at NIST, and they proposed a rather different kind of measurement, which they called well, they didn't call it this, I call it this. It turns out it's actually a parity measurement of a kind. And what I mean by parity measurement is taking -1 to some integer power. And in this case, what they proposed is taking -1, measuring -1 to the power of the number of atoms detected in their excited state. And if you take that measure, use that measure, calculate the expectation value of this operator, you find that you get this overall factor, which is irrelevant, but the important thing is you get cosine and delta t. Delta, by the way, is the omega minus omega naught. So this is, again, how you could reach the Heisenberg limit without doing all these other manipulations that I mentioned you have to do in the case of a trapped ion. Actually, Winer's group actually did this kind of measurement, in fact, with, I think, up to maybe 6 or 8 ions. I'm not sure, but it's not going to have a whole lot of ions. But they were able to do this, and they can do it partially in ion traps because you can identify the individual ions, so it's actually easy to count. By the way you would measure this thing, or the way they did it, was to actually count the number of atoms or ions in the excited state and use that number. My interest is in not necessarily doing that at all, and I'll say more about that. I just want to briefly introduce the formalism. I'll try not to do too much of this, but I want to introduce the formalism that I actually prefer to use in discussing these kind of problems, which is the Dicke states and the angular momentum, pseudo-angular momentum, pseudo-spin formalism that one can go. And I'm not going to go through this in a whole lot of detail, but you can map these product states, the symmetric ones anyway, you can map onto the angular momentum states where the J, the total angular momentum of J, which is sometimes called the cooperation number, is the number of atoms divided by 2. And so the lower state, J minus J, is when all the atoms are in the ground states. J minus J plus 1 is this symmetric combination. You permute the excited state amongst the different possibilities, all the way up to the state where everything is excited. Let's see, did I miss anything? No. Okay, so one special state that occurs is the so-called atomic coherent state, which is supposed to be kind of like the analog of the usual Glauber coherent state for a single mode field. It isn't, but it's close in some respects. And the idea is to operate with something, the operator I call R up there, which is very similar to the displacement operator. People do call this the angular momentum displacement operator sometimes. And you operate on the ground state, and you assume all the atoms are in the ground state. Operate on that, and you get this superposition of all the angular momentum states. The theta and the phi that come in here through the parameters z and xi, these are the parameters on the Bloch sphere. They parameterize the Bloch sphere. Except that theta now is taken to be at the South Pole, not at the North Pole. 0 is the South Pole. Pi is the North Pole. If I apply a pulse to the ground state, and I apply a pulse that's pi over 2 in this context. By the way, whoops, it keeps floating away on me. The atomic coherent state is just a product of the individual states of each of the atoms. We have to call these qubits now. So it's a product of the qubits, each one of the qubits in the same superposition, so it's a product of that. So there's no entanglement in the atomic coherent state. And if you apply a pi over 2 pulse to this, which is what you do in what you would do if you were doing n atoms at a time in the Ramsey procedure, then you would produce a new state as is given here, and you produce this particular, atomic coherent state, and that's what we assume that they would do in the Ramsey procedure. And here's the operator's decomposition, which does all this interferometry, the spectroscopy. And if you're interested in the difference in the atomic populations, then that turns out in this formula is going to be twice the average of JC, and you get n cosine omega minus omega naught, all times t, and that's what you get. This is basically the standard Ramsey spectroscopy done with n atoms in time. All it does is change the amplitude by a factor of n. And it turns out, I'm not showing you here, but it turns out it doesn't really matter what your initial state is, whether it's entangled or not. For this case, it doesn't matter. It comes out to be some factor times this cosine omega naught, omega minus omega naught t dependence. You can't change the anything in that argument by using some kind of a special non-classical state. Always comes out that way if you do these things collectively. If you prepare that kind of state, which, by the way, in terms of the J, the state at the top there, the J plus J minus J, that's the same as the state with all the atoms, superposition of all the atoms in the excited state with all the atoms in the ground state. That's the kind of thing that the Bollingen group talked about. And the thing about that is why they came up with this, parity method of measuring, doing the measurements, is that if you try to calculate with this state, after going through all the procedures, try to calculate the difference in the population, it turns out the average is 0, so you don't get any signal that way. And that's why they introduced this parity operator. Okay, and here's the way I write it slightly more generally. And it's interesting about this parity operator because there's no classical analog to it. It's a Hermitian operator and therefore an observable, but there's absolutely no classical analog to that whatsoever. And again, if you take the expectation value of that operator, you get basically the same thing that we had before, the same thing I wrote down earlier. I want to go back to photonics for a bit because this is, I used the proposal by Bollingen and all and adapted that idea to doing interferometry in optics, quantum optics, with the same ideas, because there are certain states that have this same property. You can't, the difference of the photon number at the output of an interferometer vanishes, so there are problems in the usual method. And so I propose this again. It just is the ETI pi times the photon number operator. Again, there's no classical analog to that. And why does this become important? Well, it becomes important. Where I got into it was to try to figure out how you could do what observable you needed to do interferometry with the so-called noon state. John Dowling's group had for a number of years been talking about noon states, and but they didn't have really any realizable operator for what needed to be measured. They had some operator that gave them the result they wanted, but they didn't have a physical implementation of this. And I was trying to figure out what would do it, and it turns out this idea of parity does it. And if I do parity measurements on only one of the output beams of the interferometer, by the way, MBS means magic beam splitter. You have to have something special go on here to produce the noon states. Beyond n equal to 2, you can't do this with an ordinary beam splitter. Anyway, so here's the phase shift, and you're trying to measure that. You do a parity measurement on the output there, and this is, whoops, I'm going in the wrong direction. What did I do? This is what you get. And the interesting thing here is that the results sort of depend on whether n is even or odd. You do get the Heisenberg limit exactly, but there's something else you can see going on here, which I didn't pay a whole lot of attention to at first. These two curves represent different photon numbers. I think this is 4, and maybe this is 20. I'm not, the blue line I think maybe is 4, and the red dash line there might be 20. But what you see is interference fringes which are super resolved, and we all thought that itself was where the Heisenberg limit was coming from, but it really isn't. The Heisenberg limit comes from the fact that the derivative in the denominator of that error propagation thing up there, function, you have to have a steep slope. You want that to be as large as possible. You have a steep slope, and that's where that's coming from. It's not coming from the narrowness of the fringes, which turns out to be a totally different effect. And the reason I know that is because John Dowling's group did something which I didn't even think to do, which was to look at ordinary interferometry with coherent light instead of doing the subtraction that one normally does. So when you do the normal subtraction, you, again, get the standard quantum limit, which is the best you can do with this kind of detection technique and with those kinds of states. Actually, with those kinds of states, that's the best you could do anyway, because it's classical light. And I thought, well, if you did parity measurements with this, you get the same thing, and that would be the end of it. But it turns out you still only get the standard quantum limit. But what you do instead, again, we're doing parity measurements on one of the outputs here. What you do instead is you get something rather remarkable, which is that you get this exponential function with n bar 1 minus cosine phi, and phi is the phase shift you're trying to detect. So if phi goes to 0, as phi is close to 0, notice you get this very narrow fringe. The blue dashed line you see there is what you get with the ordinary technique, okay? When you have cosine and so forth. But the narrow line, due to the parity measurement, is, again, super resolved. So you can get super resolution even with classical light by doing this measurement. But again, you're doing a measurement of an operator or an observable that has no classical analog to it. Oh, rats. All right, so time flies when you're talking up here. Anyway, the experiment has actually been done. I'll mention this briefly. Experiment has actually been done by a group in Hebrew University in Jerusalem, and they've actually shown this effect by doing photon number counting, and they do it with a cascade of beam splitters and so forth, with single photon detectors. I won't go into that, but the fact is they have experimental support that this can actually work. What I wanted to do is try the same thing with atomic interferometry or atomic spectroscopy, and particularly it seemed to me that you could apply this to atomic clocks, because you want to make, again, you want to make the fringes narrower. And it turns out you can do that even if the atoms aren't entangled. If I have n atoms, and I prepare them in the ground state initially, go through the whole procedure, the pi over 2 pulse, all that stuff we talked about before, and now do a parity measurement on this, look what happens. You see the n equal to 1, that curve there, is the same curve you would get apart from an overall factor, which is irrelevant in this case. It's the same curve you'd get for the ordinary spectroscopy, Ramsey spectroscopy that you would have. For one atom or n atoms, it doesn't matter. But by doing the parity measurement, though, it turns out that you can see that these fringes narrow significantly. And so we've got a few graphs up there with 200 atoms, 2,000 atoms, and so forth. So you see this narrows, and there's no entanglement. The parity involved, in this case, the expectation value of the atomic parity goes to the cosine to the n factor, to power n of that, and that's why that happens. But again, it's a collective measurement, and no entanglement is involved. If entanglement were involved, it'd become even narrower. And this is basically the same kind of curve here, except the state up top is the maximally entangled state of the atoms, and you get a very narrow curve at the middle. And if you take other states, like if you operated with JZ on the atomic coherent state, you get a so-called spin squeeze state. We don't care. We're not using spin squeezing here, which is another way to approach some of these things. But you do get entanglement, and the entanglement also causes things to narrow. And the last thing I want to mention, by the way, if I can go back here, one thing that the people at Hebrew did was do another kind of parity. They did the parity where you have the probability of detecting 0 photons versus any other number. And the bottom, let me see if I get this right here. I think the top graph is parity. Yeah, the top graph is the parity, and the bottom one is where they only detected the vacuum. And that kind of parity gives you something very similar. The results are very different. The problem is that parity works with other kinds of states very well, but the P0 does not seem to work so well with non-classical states of light. Anyway, but we did this with the atomic case, and it turns out that we can get something very close to what we get with parity in that as well. This is, again, where you start off with all the atoms in the ground state and there's no entanglement. But we can't seem to get it to work for anything else. The last thing I'll mention is that we're working now on ways to do the measurements of parity. And I look at it as, even though the standard way people think about parity is that you take -1 and raise it to the power of whatever number you've measured. But there are ways of doing, at least in principle, there are ways of measuring parity directly without first measuring any kind of number. And several years ago, we published a paper on how to do this. The problem is it requires a cross-curve medium, and the parameters for that are not really there yet, if they ever will be. But nevertheless, the procedure we outlined there, I think, can easily be adapted to the atomic case if we have a dispersive interaction coupling the interferometer, the optical interferometer here with the atoms. So that's where we are right now, and so we still have a lot of work to do on this. But we think we can at least propose ways of getting narrower fringes for the purpose of atomic clocks. So this is not at all an area I ever thought I'd be working in. So anyway, thank you. Thanks for your attention.
Any questions? Time for one. Let's thank Chris again.
Okay. Thank you.